All right, this video is to help you fill out your Piecewise Functions graphic organizer. In this video, we're going to talk about what a piecewise function is, how to evaluate a piecewise function, how to write a piecewise function if you're given a graph, and finally how to graph a piecewise function. Let's start with the definition. What is a piecewise function? For that, a piecewise function is a function with two or more rules called subfunctions that apply to different parts of the domain called subdomains. And so a lot of times what we see with a piecewise function is part of the function will be quadratic while another piece will be linear. But in reality, the pieces could be parts of any type of function. They could be cubic, they could be square root, they could be rational. And so there's a lot of different varieties. And notice it says two or more pieces. We can always have more than two. But for this graphic organizer, we're going to stick with just two. So for evaluating a piecewise function, let's use this example here in the center. So using function notation, it lists the function name, h in this case, from the example in the center, and it wants to know what the value of the function is at -3. Well, h is not a single function. It actually has two rules, just like in the definition, or two subfunctions. And next to it, it specifies what part of the domain each rule is applied. Now, sometimes you're going to see from some sources, it may have an if in here, or it instead of a comma, or it might say when instead of a comma. But the image I used here has a comma for it. So it's separating the subfunction from its subdomain. So when evaluating a piecewise function, what I have to do is consider the value of the function they want me to find in what subdomain it would fit in. This is going to help me select which rule I'm using. So in this case, they want me to find -3. And so I have to look to say, well, when is x less than, or which piece does -3 fit in? And so in this case, -3 is less than -2. And so the rule I would be applying here is just 2. There's no variation in this at all. So here for h at -3, the answer would just be 2. Now, when I go to the next one, h at 1, now again, I have to ask myself, in which piece or which subdomain would x being 1 take place? Again, my two pieces are x is less than -2 and x is greater than or equal to -2. Well, 1 happens to be greater than -2, so it's going to fall in this second rule here. It's going to fall in this second subdomain, which means I'm going to use this second subfunction or second rule. So for this case, I'm going to use my 1, and I'm going to plug it into this rule here. So the rule we're going to use is going to be, instead of x, I'm using 1 plus 2 squared. And so 1 plus 2 becomes 3 squared, and 3 squared, of course, is 9. So h of 1 would be equal to 9. Now, similarly, when I take h of 5, I've got to, again, ask myself, which subdomain or which domain of which rule would 5 fall into? Well, 5, similar to 1, is greater than -2. So I'm going to use this second rule again. And so here I would use the x plus 2 squared, but instead of x, I'm using 5. So I'm going to have 5 plus 2 squared. 5 plus 2 is 7. Again, 7 squared, and so that's equal to 49. And so that's how we evaluate a piecewise function. Now, what if we wanted to write a piecewise function from a graph? In this case, what we have to do is identify the two pieces, and we're going to have to come up with the subdomains for them. So we're going to have a subfunction for each piece that we see, and then we're going to have a subdomain for each subfunction or each rule. So a lot of times it's easier when we look at a piecewise function, at least at the graph, and think about the functions if they were to continue on. So a lot of times they're going to stop, like in this one here, we can see we have part of a parabola and part of a line. So the skill that's going to be needed here is remembering how to write the function for a parabola and how to write the function for a line. Then all we have to do is decide the subdomains for them. All right, starting from the left, from the very left. So let's call our function, let's say, name it something other than h of x. So let's call this one g of x. Call it g of x. The order that we list the rules in, or the subfunctions in, at the top should be the leftmost piece. Then if there's 3 pieces, it would be the middle piece, and then the rightmost piece. In this case, we've only got 2 pieces, so the top one's going to be the left piece, the bottom rule would be the right piece. So what I'm going to do right now is, again, I said we need to imagine as if it did not stop. So if I take this parabola here, it would, if I were to continue it, it would end up going through positive 2 right here. So it would come on up to positive 2. And then it would come on up to, looks like positive 5 right here. So it'd come up there. So it'd come on up this way. And this is just to get a better view of what's going on. So the method we're going to use here for this is we're going to use the vertex formula for a parabola. And so remember, the vertex is just this point, this absolute minimum or maximum. And the way it works is, as a side note, if you've forgotten how the vertex formula for a parabola works, or a quadratic function, it's going to be y equals, and then we'll do a, in case we've applied a vertical, shrink, or compression, x minus h squared plus k. And hk is what forms our vertex, all right? It forms our vertex. Now, make a note that it is a minus in the actual vertex form. So if h is negative itself, that's where we're going to see a plus. And this is where the transformation comes in and we say, oh, we got to do the opposite of what we see. And it's all because of this minus. So the vertex we're going to be using here is the point hk. So the vertex here in this form is just the point hk. So looking at this sample graph, I can see that the vertex down here is at 0, -4. So that simply means that the h value here is 0 and the k value is -4. So when I'm going to write this rule for my piecewise function, I am going to write it as, it's going to be x squared, because that's our parent function. So we're going to have x squared. Notice that the h would be 0, so it'd be x minus 0. So I'm just going to write it as x, so it's x squared. And then we're subtracting 4, so we have -4. And we'll come back to the subdomain in a little bit. But next, what I want to do is I want to focus on the linear piece, that second piece. We can see it's a line, so we know its parent function is y equals x. So for this one, we can see that they've changed it just a little bit, but if we were to imagine it, it would continue to fall in this direction here. Right? And so we need to determine its slope. So if I look, I can tell that I'm going up 2, I'm rising 2 and running 1. I'm rising 2 and running 1. The dash line I did, not so good, but we can get the idea. So the second rule here, I have a slope of 2, but my y-intercept would be -4. So that's kind of the point of extending it out because we need both the slope and the y-intercept. So for this equation here, what I would have is I'd have a positive 2x, I have a slope of 2. And if it went that far, the y-intercept would be -4. Now, we know it's not going to go back far enough to see the y-intercept, but we do have to include it because that's what actually defines, that's the rule for that piece. Now let's talk about our subdomains. I'm going to clear some of this writing off. And let's talk about our subdomains now. So as we see that first piece, it's coming in from negative infinity, because remember, domains always are comprised of the x values. It's coming in from negative infinity because as it goes up, it's still going to the left. And then it comes down and x stops at +1. So what we're going to say here is this rule is applied anytime that x is less than or equal to 1. And then for our second subfunction or piece, we can see that we have an open circle there at 1, and then it continues on to positive infinity. So it goes up and it keeps going to the right. So in this case, because it's not equal to, we have x is greater than 1. And so we have a function, a piecewise function for that graph. That is a piecewise function for that graph. Notice this is different from the example there because I wanted to show you something different, because in the last piece here of the graphic organizer, we're going to graph that function. So essentially, we're going to do just the opposite of what just occurred. And so now we're going to graph the piecewise function, and we're going to use h of x. So yesterday in the video, the person recording it suggested creating tables of values, and I think that's probably the best thing to do. So again, like he said in the video yesterday, if you notice, this is a constant function. So you really don't even need to create a table of values for a constant function. All right? You don't even really need to create a table of values for it. We can see that anytime x is less than -2, so the fact that it's less than -2 means I need to use an open circle for it. The value of h of x is just going to be 2. So if I come down here, we got x is -2, so I come up, I'm going to put in an open circle here. And as long as x is less than -2, the value of the function is 2. And since it just says less than -2, that means this thing is going to go on back to -infinity. So there's the first piece to this piecewise function. We've graphed it for that domain. Now, the second piece is going to take a little bit more work because it's not a constant. And in fact, this is a quadratic. So like he said in the video, what I'm going to do is I'm going to go ahead and create a table of values for it. So notice it says when x is greater than or equal to -2. So what that means is we're going to pick some values. We're going to start with -2. And we understand at -2, it's going to be solid because it says greater than or equal to. And I've got to think of values that are greater than -2. So I could go ahead and use -1, 0, 1, and 2. And then our rule for that is whenever x is greater than or equal to -2 is x plus 2. X plus 2 squared. So let's see, -2 plus 2 would be 0. 0 squared would be 0. -1 plus 2 would be a +1. +1 squared would be a +1. And so we have 0 plus 2 would be 2. 2 squared would be 4, so that one would be 4. I have 1 plus 2 is 3. 3 squared would be 9. And then 2 plus 2 would give me 4. 4 squared would be 16. And that's going to be off the top of our graph. So we're not going to end up graphing that last point. But this gives us plenty of points to be able to sketch the second piece of our graph. So I'm going to start at -2, x being -2, and I see that I have a y value of 0. Now, we indicated that it needed to be a solid point because the subdomain here was greater than or equal to -2. So I have the point -2, 0. Then we have -1, 1. So we're right here. Then we have 0, 4, right there. And then we have 1, 9, which for us would be somewhere like right up here. And as I said, I'm not even going to bother with that last point because it's way off of our graph, the 2, 16. So now what I'm going to do is I'm going to come in and I know what a parabola looks like. And I know that based on the rule for it, it is just a parabola that's been shifted to the left 2 units. That's what the x plus 2 is doing. So when I look at this, I know that the vertex of this thing is -2. Remember, it's the opposite of that sign, but then there was nothing outside of it, so we didn't move it up and down. So I knew what the parabola is supposed to look like, and there I've completed my graph. And so this completes the graphic organizer for piecewise functions. If you have any questions, you can go back and watch the video again, or you can ask me in class.